Okay, so welcome back everyone to CS794 CO673. So this is our second lecture, and we will start talking about our first algorithm, the gradient descent algorithm. So the problem we're interested in solving in this lecture is minimizing an unconstrained smooth function. So I highlighted the important thing here. So unconstrained meaning that there's no constraint on the variable we're trying to minimize. And the function f, usually called an objective function. So this is what we want to minimize. So the objective function is smooth, meaning that it is continuously differentiable. Okay, we'll be more precise about what do we mean by a smooth function, but for now, you should think of this function, you can take derivatives. Okay, and we'll consider both convex and non-convex functions f. Okay, so to give you an example from machine learning, we look at the linear least squares regression problem. So this is a problem where you are given a data set consisting of n pairs of points. So you're given xi, which is a feature vector, and yi. Okay, so here xi is usually a vector in d-dimensional, and yi is just a number. Okay, and our goal is to find a prediction function such that f applied on xi will be approximately yi. Right, so this is what we want to learn in this regression setting. And in the linear regression problem, we assume the function f is a linear function. Okay, so this is written here. Basically, you give me the feature vector x. I'm going to compute the dot product with respect to a weight vector w, and then I'll add a bias term. Okay, and if we want to visualize this, so you have a data set in the two-dimensional case. Now you may have some points, right? So the x-axis, and you have a y-axis. So you have a bunch of points, and the hope is that we want to find here we go. We want to find a line. Right? This is our linear function that sort of goes through most of the points. Okay, and this is our b, the bias term, and then we have a normal vector w. Right, so this is how we parameterize the linear function. Okay, and typically in machine learning, people do this padding trick where you just attach 1 to x, attach b to w to make the notation a little bit simpler, right? So we can just rewrite everything as a single dot product or inner product. Okay, so this is what we want to do, and we're going to rephrase this as a least squares linear regression problem. Namely that we're going to minimize this function here. So basically we want fxi, which is xi dot product w now, right? We want this prediction to be close to the choose yi. We just minimize their square difference, okay? And we sum over the entire data set. And you can rewrite everything in the matrix form, right? If you put all the xi's into a matrix, and then you put all the y in a vector. There's a typo here, so this should be a vector y. And then you can rewrite our least squares problem in this quadratic function here. Okay, so this is our objective function f, and it's clear from this example that the function f is continuously differentiable. In fact, you know the derivative of this function. So if you go back to the previous lecture where we had an example on how to compute the gradient of a quadratic function. Okay, this is a quadratic function here, and there's no constraint whatsoever on w. Right, you are free to find any w and b as long as you can fit the data well. So our linear least squares problem basically looking at this sum of these distances, and we minimize it. Okay, so what algorithm can we use to solve this problem? For the least squares problem or the linear regression problem, we don't really need gradient descent algorithm because they are better algorithms. But for a motivating perspective, this is a perfect example. So let's look at the gradient algorithm that we can use to solve this problem. Okay, so we've already seen this algorithm last time in a more general setting. So here we just specialize everything to gradient descent. So the algorithm is extremely simple. So first, you find an initializer W0, right? So you got your W0 here. It can be anything, just pick it randomly. And then you're going to compute the gradient at the current point. And you're going to choose the step size. And then you're going to compute the iterate, the next point, Wt plus 1, by subtracting the gradient from your current update or current iterate Wt. Right? So it's extremely simple algorithm. If you want to implement this, it takes you 4 or 5 lines. And why this makes sense? Well, we have seen this last time, right? If you do a Taylor expansion, so you plug in our update to the objective function f, and then you do a Taylor expansion, you get to here, and then you realize if your step size eta t is small, and because the norm here is positive, then you can actually decrease the function value f, right? You can decrease this function value at the next iterate, unless the gradient is 0, right? If the gradient is already 0, then you may not be able to decrease. But other than that, you can always strictly decrease the function value. Okay? And I want to emphasize that this is a good progress, but not necessarily enough progress. Okay? Decreasing the function value may not give you any guarantee yet. Okay? We'll see an example later on. And then for choosing the step size, there are 3 ways of choosing step sizes, at least in the context of gradient descent. So there is this Cauchy's rule, where you basically find the optimal step size, right? So you look at the ray along this gradient descent update. You find the optimal point in terms of the minimum function value along that ray. And Curry's rule is very similar to Cauchy's rule in the sense that Curry only requires you to find a local minimum. You don't have to find a global minimum. Okay, you find the minimum, the smallest local minimum of either. And last but not least, the constant rule. So you just put the step size to be a constant. And this is actually the most used one in practice. And we're going to see how can we set this constant in a minute. Okay, so that's it. This is our first algorithm, the gradient descent algorithm. And we're going to analyze this algorithm a little bit. And in particular, we're going to focus on the constant rule. Okay. And before that, I want to recall this necessary condition for finding a local minimizer or local maximizer of a differentiable function. Okay, so if you want to minimize a differentiable function f, then you know at the minimizer, at the local minimizer, so we defined local minimizer in the previous lecture. So it must satisfy this equation. So the gradient must vanish. Okay, so the important thing is there cannot be any constraint on f. The function f has to be differentiable, which is perfect for the gradient descent algorithm, because the gradient descent algorithm is proposed for minimizing unconstrained and smooth function, right? So in other words, we can check the progress of our gradient descent algorithm by checking whether or not this equation, this necessary condition, is satisfied or close to be satisfied. Okay, in fact, any point that satisfies this equation is called a stationary point, or some people call it a critical point. Okay, and you can easily construct examples to show a stationary point may not be a local minimizer, but if the function is convex, then it is any stationary point is actually a global minimizer. Okay, the example to keep in mind is the following. Okay, so you can have a quadratic function like x cubic, and you have a point here. My drawing is not perfect. Right, so this point here, x3, if you take the gradient at 0, the gradient is 0. Okay, but this point is not a local minimizer, because if you look at the neighborhood, it's not a local minimizer, it's not a local maximizer, it's called a saddle point. Okay, so this convinces you that satisfying the necessary condition is not a guarantee for being a local minimizer or a local maximizer, but any local minimizer has to satisfy this condition. And as you can see, for non-convex functions, in some sense, this is the best we can do, and this is why we're going to show the gradient descent algorithm will drive the iterate towards satisfying this equation. Okay, so I'm not going to prove this necessary condition here because it's fairly standard. It's a first year calculus exercise. If you haven't seen this before, please go through the proof by yourself. Okay, and here's an example where by strictly decreasing the function value does not guarantee convergence even to a stationary point, let alone a local minimizer or local maximizer. And you should also check this exercise, this example by yourself. I put enough details there. You can follow by yourself. Okay. All right. Okay, I want to emphasize that this counterexample here is a common mistake. Now you can see people even in good papers where they make similar mistakes. And so when you decrease the function value, that is not enough to say the algorithm will converge to a stationary point. It's not true. Okay. And my favorite sort of analogy to this is, imagine there's a turtle, right, who wants to go. If you have a race, let's say the race has 1.10 meters, and the turtle will go 0.5 meters first, and then it will go, or every time it will go half of the previous length the turtle went, right? So next time it will go 0.25 meters, and so on and so forth, right? And in each time step, the turtle will make strict progress, right? But the turtle will never hit the finishing line. Okay, the similar thing here. Okay, strictly improving things does not guarantee convergence to a stationary point yet. You need other conditions. All right, so next we have a theorem. This is actually probably the first convergence proof theorem for gradient descent. This is done by Curry in 1944. And the interesting thing about this paper is that Curry was actually working in UK in Arsenal, where they actually use the algorithm to adjust designs of canoe during World War II. Okay, so it really has practical value, this algorithm. Okay, so as you can see, I put the theorem in gray, meaning that you don't have to go through the proof or the theorem. Nevertheless, I put it here just to show you that that this theorem or the proof is not trivial. Okay, it's actually quite tedious. And the nice thing about this theorem is that you only need the function to be continuously differentiable, and you can use this Cauchy or Curry's rule. Okay. So for now, most people in machine learning, for instance, they do not use Cauchy or Curry's rule because it's quite expensive, and this is why we don't even bother going through the proof in the lecture. But if you're interested, you should take a look by yourself. In particular, you should try to understand this orthogonality condition, because in many counterexamples, when people say gradient descent is slow, you usually see people draw the zigzag trajectory of gradient descent, right? So you have a gradient descent, goes here, and then goes here, goes here, goes here, goes here, goes here, goes here, right? It zigzags towards a local minimizer. So why does the algorithm zigzag? The algorithm zigzags precise because if you choose your step size well, you're going to satisfy this orthogonality condition, right? So the previous step and the next step is going to be almost orthogonal to each other. This is why you see the zigzag behavior. Okay, you can actually show this, prove this. All right. Okay, and as you can see, the proof is long. I cannot even fit it in one page, so we're not going to discuss that. And this is another proof for Cauchy's rule by Polyak in 1960s. The proof is much simpler and much easier to understand. But again, as I said, we don't use Cauchy's rule nowadays, so I'm not going to go through the proof either. But if you're interested, you can check this by yourself. All right, so now I'm going to discuss a very cool lemma. Okay, and we're going to use this lemma again in this course. So it's very crucial that you understand it. Okay. And in my note, I tried to state the results in the most general form. This inevitably will force me to use some notations that may not be familiar to you. So in particular, here we have one notation, this norm with a circle. If you go to the previous lecture, we actually define this norm. This is a so-called dual norm of a norm, right? So to help you recall, the dual norm, let's say G, is defined as the maximum over the dot product X and G, and then you put X norm smaller than 1. Okay, this is the definition of the dual norm. And if this is too much, you can always think of the dual norm and the original norm as the true norm. Okay, if this is too much for you, just make this substitution. You can still understand the main idea. Okay, so what does this descent lemma say? It basically says if your function, in particular, if the gradient of the function satisfies a strong form of continuity, then the function value satisfies a quadratic upper bound. Okay, in some sense, if the function is too smooth, then it starts to look like a quadratic function. This is all it says in this descent lemma. Okay, so I'm not going to go through the proof of the descent lemma here. So this is a fairness easy exercise from calculus again. I put enough details here that you can verify by yourself. Okay, but I want to mention the next result, namely that if I give you a function, how do you recognize if a function is L smooth or not? Okay, so first let's define what is L smoothness. Okay, you probably have seen this before if you have read any paper that deals with optimization. So L smoothness means if I have a function f that goes from Rd to R, right? I'm going to say the function is L smooth if I take the function f, w plus z, any arbitrary 2 points w plus z is smaller than f of w plus the gradient of w dot product w plus z minus w gives me z, and L over 2 z squared. Okay, sometimes people write things like this. This right, fw. Okay, let me change this w to z smaller than f of w plus the gradient of w, and then you have z subtract w, and then you have L over 2 z subtract w squared. Okay, the two are exactly equivalent. It's just a simple substitution, right? So if you substitute w plus a to z, you get the same. Okay, you get, so they're exactly the same. So what it means is, if you look at the function in terms of z, okay, then the function of z is upper bounded by the right hand side here, and the right hand side here now is a quadratic function of z, because f of w is a constant in terms of z, right? The gradient of w is a constant vector in terms of z. So really this is a linear function here, and this is a quadratic function of z. Okay, so the L smoothness is basically saying your function can be upper bounded by a quadratic function. And you're going to see why this is important. Okay, in fact, this is in some sense equivalent to the gradient descent algorithm. All right, so how do I know, if I give you a function f, how do I know if it is L smoothness or not, right? Well, this is how you can check. So the theorem, basically the proposition 2.11 here, that basically says, if you look at the gradient, or if you look at the Hessian, okay, so you compute the Hessian of f. So the Hessian of f is a matrix, right? It's a d by d matrix. And if you look at the spectral norm of the Hessian, so basically, if you look at a spectral norm at w, and you have to take a maximum over all possible w, and this is defined as a maximum over w, and the maximum, let's say, over z, the norm smaller than 1, and then you have the Hessian, which is a matrix, multiply the vector z, gives you a vector, and then you take the 2 norm of the vector. Okay, let's say everything here is a 2 norm. Okay, so if you know linear algebra, the spectral norm of a matrix is basically the maximum singular value of that matrix. Okay, so and the proposition 2.11 and proposition 2.10 basically shows you, if the spectral norm of the Hessian is smaller than L, then this direction holds. Then the function f is L smooth. Okay, so if you combine the two propositions, this is what the what they say. So in order to check if a function f is L smooth or not, just compute the Hessian, you get a matrix, compute the spectral norm of the matrix. If the spectral norm of the Hessian is bounded by L, then the function f is L smooth. Okay, and the converse is also true if the function f is convex. Okay, for non-convex functions, the converse may not be true. And the proof basically boils down to the definition of Hessian. Okay, so we actually had the definition in the previous lecture, but this is a little bit abstract. So if you define the Hessian in terms of in the abstract form, then you just manipulate the definition using triangle inequalities, and you can prove the result. Okay, it's fairly standard, and even if you don't understand the proof, it's fine, because this is a fact. You can memorize the fact, and then you're going to see how we're going to use this fact in the proof of the gradient descent algorithm. Okay, all right. To summarize, what we have shown is we have defined when a function f is L smooth, and we can verify when a function is L smooth. So f is L smooth if the Hessian with the spectral norm is bounded by L, or equivalently, if the gradient of f is L Lipschitz continuous, meaning that if you take two inputs on the gradient, is going to be bounded by the difference in the input. Okay, so the difference in terms of the output is bounded by L. The difference in the output is bounded by L multiplied by the difference in the input. Okay, so the L-Lipschitz continuity is very important in a lot of problems in machine learning. So here we're going to see how we can use this for proving the convergence of gradient descent. Okay, so and now we have an example where the linear regression example that we saw before, right? So we have our objective function here. So you can expand the L2 norm to get the quadratic function. And then you can use the Hessian formula from the previous lecture, and you can verify the Hessian is 2 over n xx transpose. And from here, it is immediate that the function f is convex because the Hessian is positive semi-definite. And it's also clear that the function f is L smooth with the constant L to be the spectral norm of xx transpose and multiply the constant 2 over n. Okay? And the problem is computing the Lipschitz constant L can be very expensive. First of all, you have to compute the product xx transpose, right? That's already, like if your data set x is big, that already will take forever. And then you need to compute the spectral norm of a matrix, a big matrix. That's also very expensive. Okay, so one hack that people usually do is they replace the spectral norm with the Frobenius norm, and then they can subsample your data set and compute the Frobenius norm. Okay, but later on we're going to see a better way to do this. All right, so we have an example where we can verify the function is L smooth, right? All right, so now we'll come to our main result of this lecture. Okay, so we're going to prove gradient descent converges for L smooth functions. So we have two assumptions. One is the function is L smooth, that is standard now, and the function is bounded from below, meaning that the minimum value of the function does not go to minus infinity. Okay, so the function is bounded below. So we're going to choose a step size eta t at the tth iteration from an interval. And you're going to see why we choose this interval in a minute. And then the claim is that the iterator of the algorithm, its gradient will go to 0. In fact, you can prove the minimum gradient along the trajectory will go to 0 at this rate. Okay, I'm going to explain what does this rate mean in the end. But for now, let's look at how we can prove this. Okay, so it's actually quite simple. You go back to our definition of L smoothness. So if the function f, we're assuming the function f is L smooth, so we can actually expand the function. So this is f of the next iterated w after the gradient descent update with step size eta, right? I'm going to expand this. I'm going to choose, this is w, this is z. I'm going to apply L smoothness. So I'm going to get, if I'm writing all the details, so I'm going to get the upper bound f of w plus the gradient of w, and I'm going to take this, subtract w, I'll get a minus eta, the gradient of w, and I'm going to get 1 over L, and I'm going to take this term, subtract w, I'll get minus eta, the gradient, right, squared. And then if you rearrange, this is just the norm, this is the norm, you get what I wrote here. Okay, so nothing fancy, it's just the definition of the L smoothness. And then we realize if this term here, if this term is positive, then we actually decrease the function value by doing the gradient descent step, right? So when is this term positive? Well, it is either 1 minus L eta divided by 2. This is positive if, let's say, eta is greater than 0, and then 1 minus L eta over 2 is greater than 0, that means eta is smaller than 2 over L. And this is why you see we have this condition. Okay? And this justifies why we choose the step size in this manner. Okay? Because if you choose your step size in this manner, after one gradient descent step, you're going to strictly decrease the function value. Unless the gradient is 0. It's already 0. Okay? Alright. So, good. So we are decreasing the function value. And now, let's rearrange the inequality we have. Okay? Let's just move this term to the left, move this term to the right. Okay? And then you will realize we arrive at this part. Okay? And nothing fancy, just rearrangement. So now what I want to do is I want to do telescoping, right? So you realize that we have this term in the numerator. Now if I sum the numerator, I'm going to get f of w1 subtract f of w2, and I have the next term f of w2 subtract f of w3, and so on and so forth, right? And this will allow me to telescope, to cancel lots of terms. This is what I want to do. The problem is, if I do a summation over t here, the denominator also depends on t. So I cannot naively telescope the numerator. So what do? Well, I first try to make sure the denominator will not depend on t. I just use the bounds I can have. For instance, I know eta t is greater than alpha, sorry. So if I replace eta t with alpha, I will make the denominator smaller. And because everything is positive, then you take the inverse, it will make the whole term bigger, right? So this is why I can replace eta t with alpha. And you do the same thing with eta t here. If I replace eta t with the upper bound, then because of the minus term and then the inverse term, I get upper bound in the end here, right? And from here now it's clear the denominator does not depend on t anymore. So I just do a summation over t from the left hand side, a summation over t on the right hand side, and I can telescope, right? So this is what we did here. I telescope, and finally we know f of wt is greater than the minimum value of the function, right? Any point is better than the minimum value, and the minimum value is finite. So this is our assumption, f star is finite. So I can just replace this term with f star and get something bigger. All right, and that's it. This is basically our proof, because now you realize the right hand side does not depend on t, the capital T, the number of steps you're doing at all. So you can take the limit on the left hand side, right? If I take the limit, that t goes to infinity, it is still bounded by the right hand side, because the right hand side does not depend on t. And this basically means this sequence of the gradient is square summable. You take a square of each gradient norm and you sum them up, it's finite. And this immediately implies the gradient has to go to 0, right? If you have a sequence where you can sum them up, you have a positive sequence, you can sum them up, then the sequence has to go to 0. Otherwise, the sequence will diverge to infinity, right? Okay, so this is what we have proved. The gradient of the gradient descent will converge to 0. And it's also clear that this bound holds. And this is because we have a summation. The summation is obviously greater than the number of terms multiply the minimum. Right? So if I have a sum of terms, it's greater than the number of terms multiply the minimum value there. Right? This is clear. And then if you move t to the right hand side, you get what is claimed in here. Okay? All right, so that's basically our proof. As you can see, it's extremely simple. It boils down to basically the definition of L smoothness. Okay? And you can also optimize the bound. Right? How do you choose alpha and beta? You choose alpha and beta to minimize this bound. In fact, the optimal choice is alpha and beta equals 1 over L, and the bound has this form. Okay, and this bound makes a lot of sense because first, if you look at the dependence on L smoothness constant L, okay, if you have a function where L is bigger, what does that mean? Well, if L is bigger, that means your Hessian is bigger, right, in some sense. And the Hessian means the change of the derivative. And if the derivative changes fast, your function is oscillating, very fast. In that case, you will have to use a smaller step size because you don't want to overshoot. So the step size becomes smaller. The step size 1 over L becomes smaller, and because the function is much steeper now, right? It also makes sense in the second term here as well, because if my initialization W0 is very close to the minimum value F star, right, then my algorithm should converge faster. And indeed, the bound will become smaller if your initialization is better. Okay. And also, one thing that machine learning people like the most is that if you look at the convergence rate here, it doesn't depend on the dimension of W. So W is in a D dimension, right? F is in RD. But if you look at the bound does not depend on D at all. It depends on the Lipschitz constant of the gradient or the and it depends on how you initialize, right? But it does not depend on the dimension. And in many machine learning problems, the dimension is huge. You could easily have a billion parameter. So D can be a billion. And if my bound does not depend on the dimension, then it's likely that I can use this algorithm for very high dimensional problems. Okay. And lastly, we have this 1 over square root of t dependence. Okay, so this means if you run the algorithm for t iterations, then the scale of the gradient is roughly 1 over square root of t if we drop all the constants. And this rate is in fact close to optimal. Okay, so what do I mean by close to optimal? So maybe in a few lectures we will discuss, under what setting, what is the optimal rate you can achieve for any algorithm you can come up with. Okay. All right. So that is our first algorithm and first analysis. I hope this is manageable. And you can do some comparisons by comparing the result we have here in this theorem and also the results that we skipped for Cauchy and Curry's rule. Okay, there is some difference, but for us it's not that crucial, so I'm going to skip this part. And there are also counterexamples to show all the conditions that you have seen in this theorem. All the conditions here, like L smoothness, bounded from below, the step size has to be in this way. All these conditions, you cannot relax them appreciably. Okay, for instance, if you choose the step size to be 2 over the Lipschitz constant L, then the gradient algorithm may not converge. So you can, in fact, we have already seen the example, basically in example 2.6. And also, if there's no minimizer, then the iterated WT itself may not converge. So what we prove is that the gradient will converge to 0. But we did not say anything about the sequence WT itself. Okay? So in fact, you can construct these weird examples where the gradient converges, but the iterated WT itself will not converge. Okay? And in fact, if you want to prove the iterated WT converges as well, you need to put a little bit more assumptions on the function f. Basically, the function f has to be constructible in some sense. So if I have time, we may come back to this in later lectures. All right, so now I'm going to give you one explanation of the gradient descent algorithm. And from this explanation, you'll see why we used L smoothness. And then you can immediately generalize the algorithm. And then you can actually see how to choose the step size very efficiently. Okay, so the key is again to go back to the definition of L smoothness. So this is what I wrote, the definition of L smoothness. Okay, so Wt is my current iterate, and then look at an arbitrary W, right? I can bound the function by the quadratic here. Nothing fancy. And then instead of minimizing the function W, this is what I want to do. I want to minimize the function f, right? I'm going to minimize the upper bound here. I'm going to minimize the quadratic upper bound. And I'm going to call the minimizer to be my next iterate. Okay? And the cool thing is, if you minimize this upper bound here, because there's no constraint, and in fact this is a convex function, so you can just take the derivative, set the derivative to 0, right? So if I take the gradient here with respect to w on the right, so what I'm going to have is the gradient of f of wt for this term here, the gradient, and for the gradient here, I'm going to get 1 over eta t and w minus wt. Okay, so you should do this, verify this by yourself. And then if I solve this, I get w equals wt minus eta t of the gradient. Okay, so this is what I wrote here. So you see, the gradient descent step is derived by minimizing the quadratic upper bound in our definition, L smoothness definition. Okay. So now, once you realize this, you can actually generalize the algorithm. For instance, well, we used the Euclidean norm here. What if I use a different norm? Right? I can call a function L smoothness by changing the norm. I can still call the function L smoothness, but now with respect to a different norm, for instance, right? Like what I wrote here. And I can still optimize, minimize the the left right hand side. Okay, and I get my iterate. I can do the same thing. And the interesting is, if you do this, and if you go back to the proof we had before, this simple proof here, okay, everything still goes through. Okay, so now you can immediately generalize gradient descent from the Euclidean norm to any other norm you like. Okay, so I wrote the update here in a very weird notation. So basically, what you have to do is you have to take the dual norm of the norm you chose here, and you square it, divide by 2, and then you need to take the derivative of this guy and put it in front of the gradient. Okay, if you don't understand this, that's perfect fine. Okay, we don't need to use this in later lectures. But in case you're curious, right, by interpreting the gradient descent as minimizing the quadratic upper bound, you can immediately generalize the algorithm. And the benefit of doing this is that by changing the norm here, you may change the parameter L significantly. Okay, so later on I think in 4 or 5 lectures down the road, we're going to see this again. Okay, all right. So one exercise for you here, before I forget, is if you choose this norm to be the infinite norm. Okay, so now this here is going to be the infinite norm. And if you do this, then the direction you're going to pick, so this is infinite, the direction you're going to pick is basically the sign of the gradient. Okay. Sorry, this is the one norm. The direction is going to be the sign, and this is what's known as the sign gradient descent. Okay, and this gradient descent algorithm variant is actually useful in a lot of settings as well, because it sort of ignores the size of each component in the gradient. It only uses the sign, therefore it's more robust, especially in stochastic and distributed settings. Okay, so we may come back to this later on. All right, so Gradient descent is minimizing the quadratic upper bound in the definition of L smoothness. Another important observation we can make here is that by exploring this observation, we can actually come up with a choice of the step size. And this is first realized by Amijo in 1966, and this is usually called a backtracking idea. Okay, so it's basically here our second observation. The first observation is that because gradient descent is descending, right? If you choose the step size carefully, the algorithm is always descending. So when you compute the L smoothness, you only need to look at W in the sub-level set. Okay, so this is sort of a minor observation. But the more important observation is here. Like, how do we choose step size? Okay, so the idea is if we go back to our interpretation of gradient descent, so gradient descent is minimizing this quadratic upper bound here, right? And how do you know this is an upper bound? Well, you know it's an upper bound because your step size is small. You choose a sufficiently small step size, right? So that this term is big enough to upper bound the original function f. But how small is small? How do you know the step size you choose is small? Well, the key is I do not know if the step size I choose is small enough, but I can actually check if this inequality is satisfied or not with the chosen step size. And all I care about is this inequality has to be true, right? So I can actually test this inequality. And this is the idea behind Amijo's backtracking line search. So what you do now is I want to choose the step size eta t such that this inequality holds. So what we're going to do is we take the update of my W. I'm going to put it in W, right? So okay, I'm going to do this with the 2 norm here. Okay, so I'm going to take the update. I'm going to plug in. What I'm going to get is f of W minus eta. So I do not know if eta is good enough. I just plug in things. Okay, I'm going to ignore the subscript t. And the right hand side is going to get f of W. And then I'm going to get this term. Put it here. You are going to get is a typo. So you are going to get minus eta t and the gradient, right? Square. So I'm going to ignore the subscript t throughout. And in the last term, we're going to get eta over 2 and the gradient squared. Okay, and if you combine the last two terms, you get eta over 2 squared, right? So the problem is I do not know if this inequality holds. Like, I do not know with this step size eta. I do not know if this inequality is true or not. What do I do? Well, but I also know if eta is small enough, then this inequality is true. So what do I do? Well, I just start with the step size eta. I can compute the left hand side. I can compute the right hand side, right? And then compare them. Do they satisfy this inequality? If they satisfy this inequality, good. I'm going to move on to the next iteration. If it does not satisfy this inequality, then what I do is I'm going to decrease the step size eta. I'm going to decrease the step size eta by half. And I'm going to check everything again, right? I just keep checking this until the inequality is satisfied with a sufficiently small eta. And that is the idea behind Amijo's backtracking. Okay, so it's written here. Basically, you repeatedly check this inequality. You find the smallest step size such that this inequality holds. Okay, and once you find that, this eta over 2 over k minus 1 is your legitimate step size. And using this, you are going to satisfy this inequality. And you can easily show, as long as k is greater than this constant here, you're going to satisfy this inequality all the time. Okay, in other words, by doing backtracking, you do not need to know the L constant here. Okay, because if you look at this inequality that we're trying to test, nothing involves L. Everything can be computed. Okay, but in theory, all you need is to test this inequality by at most these many steps or these many times. Okay, the implication of doing backtracking is that first, we may increase the bound in our convergence proof. Now, if we go back to the bound here, this is the optimal bound when we choose the step size optimally. But if we do not choose the step size optimally, we're going to increase or worsen the bound by a constant factor. Okay, no big deal. You might be slower by 3 times or 4 times, right? We don't really care much about the constant for now. And doing backtracking is really easy. All you need to do is to evaluate the function value, right? So there's a typo here again. So you only need to evaluate the function at these points. Okay, so you need to evaluate at W once, you need to evaluate the gradient at W once, and you need to evaluate the function value capital K times, right? So this is the price to pay. You have to evaluate the function a number of times in order to test this inequality. But the potential gain is also huge, because if you use the L smoothness parameter as your step size, like 1 over L, because L typically is big, very big, so your step size will be super small. But if you use this inequality, the step size you're going to use is sort of adaptive, right? Depending on where I am now, I'm going to use the local smoothness parameter L, and that local parameter can be much smaller than capital L globally. Okay, and this is especially true in the beginning phase of your iteration. All right, so that is a very cool idea to avoid computing the Lipschitz constant L, and yet you can run the gradient descent algorithm with an adaptive step size eta, and usually it actually runs faster than choosing a constant step size or fixed step size. Okay, all right, so the last thing I want to mention is a counterexample here where we have a gradient descent algorithm. We apply it to this function here, this very simple function here, and if you do the calculation, the gradient is here, the hashing is here. So this function has 3 stationary points, and one of them, namely 0, 0, is a saddle point. It's not a local minima, it's not a local maxima. And if you start in this subspace, basically the x-axis, then you're going to converge. If you apply gradient descent, you're going to converge to this saddle point. Okay, so that seems bad, right? So I can find regions where if you initialize in that region, and it doesn't matter how you tune your step size, you are going to converge to a saddle point of the function f. But the very recent result, or fairly recent result, shows that such bad initialization has actually measured 0. Okay, so this basically means if you initialize your W0 randomly, okay, then with probability 1, you are not going to converge to this saddle point. Okay, so this is a very cool result that sort of justified why you should randomize your initialization when you run gradient descent. Okay. All right, so that is all I want to discuss for this lecture. So we saw a gradient descent algorithm, and we analyzed how the algorithm performs on an L smooth function, not necessarily convex. Okay, and we proved that the gradient of the iterate will go to 0 at the rate 1 over square root of t, where t is the number of iterations, right? We also discussed how we can choose the step size adaptively without actually knowing the L smoothness parameter. Okay, so next time we're going to see how we can adapt the gradient descent algorithm when there is a convex or non-convex constraint, right? And we're also going to see how the algorithm performs when your function is convex. Can you improve the convergence rate? Can you prove the algorithm will actually converge to a global minimizer? Okay. All right, so that's all for today. Thank you for listening.